hello to each other this morning on the topic of filtering. And as I said before, filtering is in the domain of spatial information. So filtering is one of the ways of the approaches through which you can extract spatial information from a data set. This is not the only possible approach, naturally. Especially in the domain of spatial information, there are many other algorithms and approaches that were mutuated from computer vision. Okay, so spatial information is richer for higher resolution data, for higher spatial resolution data. I mentioned briefly this connection when we discussed the issue of resolution. Remember, in the lectures yesterday, I said when you increase, when you refine the resolution of the data sets, or when you consider data sets of finer resolution, you're implicitly collecting more spatial information because you're creating more spatial samples, and you're getting additional capability to see smaller spatial details. Okay, so generally, the general rule, if you wish, is you go for fine resolution data sets when you intend to leverage spatial information, or you go for coarser resolution data sets when you intend to leverage spectral resolution. Okay, this is a general consideration, but it's also supported by technical considerations. Generally, systems pursue high spatial resolution or high spectral resolution, but not both at the same times, because there are technical reasons why it is increasingly difficult. Okay, so it is achievable to get high spatial resolution. It is achievable to get high spectral resolution. That is called hyperspectral data. But if you want to do both at the same time, it's twice the challenge, if not more. So you will notice when you look at real-world data sets that generally hyperspectral data sets come at the coarser spatial resolution. Okay, so you have in some way, this decision to make about how much of spatial and how much of spectral information you want to leverage for your application, and then you decide the data set consequently. Okay, now back to spatial information. I said filtering is one of the possible approaches, but there are others. When you leverage spatial information, you can source methods from where spatial information is largely exploited, which is in computer vision. So edge detection is typically one case where you have an approach, an algorithm which was born in computer vision, but then it was mutuated in Earth observation and data processing. What is edge detection? What are edges in the first place? Edges in an image, talking about image, because as I said, this was born in computer vision, which is about images, not remotely sensed data sets. In an image, an edge is an area which basically separates two homogeneous regions of the image. The two regions are homogeneous in themselves, but are different with respect to each other. So finding the edge means finding where one region ends and then the next one starts. As I said, so this is a map of edge. This is a mask. This is what we commonly call a mask image in Earth observation, but I understand this is a common term also in computer vision. What is a mask image? It's an image where you just have two values. which may be the result of thresholding, or it may be the result of applying other features with, other feature extraction techniques with a binary result, where you have just two categories, typically background and relevant object. In this case, the relevant objects are the edges, and so we have the value, for example, value 1 on the edges and the value 0 elsewhere, meaning that this is background, this is not interesting. Okay. So the spatial information in this case is extracted through the identification of the edges. So the place where you're switching from one homogeneous region to another one. It's spatial information because it relates with the location. It relates with the connection between adjacent pixels. So this is a sibling of these others. This is a sibling of these others, but they do not relate to each other. So by comparing them, I can identify that there's an edge there. This is naturally spatial information. Notice that, again, I'm not saying anything about spectral information. I'm just reasoning on location and differences in space. As I said, this is something that is very common in computer vision, but it's also largely used in Earth observation data sets. And once again, let me point out that when we leverage spatial information, we generally give up spectral information, and we reason on one band. So even this is a multispectral, remotely sensed data set, of which we only took one band, okay, because we are not interested in finding, we're not interested in investigating the spectral depth of the image. We're not interested in investigating the spectral response of this length cover here. We can take a shallow portion of the data set and rather look at the, how can I call that, horizontal relationship between pixels. Who is next to who, and what is the difference in values. So you ignore the other bands, you take one which you deem may serve best your purpose, and then you apply an edge extraction approach, which can be taken as is from computer vision. One typical case is the Kenny edge detector. It's very popular in image processing. It became popular also in in Earth observation data processing. Obviously, for any classical, let me discuss this briefly here. It's obvious that these basic feature extraction algorithms may be considered obsolete because, I mean, what is the modern approach to, what could be a modern approach to extracting edges? It could be simply, okay, train a network which will learn how to extract edges, and you're done, okay? Now, take into account a couple of things. One is the fact that you need training data. And remember, I told you one of the pains in Earth observation data processing is the lack of training data. There are many initiatives out there distributing data and corresponding reference data that can be leveraged. But my experience is you go there, you download the data, and it's never perfectly okay. There's always something missing. It never fits perfectly your purpose, et cetera, et cetera. So you're generally left without sufficient, without suitable data, suitable training data for exactly your purpose. And then the second point is, even if you could, in principle, flatten the problem using a deep learning approach, it's somehow a brute force approach to the problem. So you put much computational power into it, as much as you need, and ultimately you will be extracting the edges. The network will have learned how to extract the edges. But you can put much less computing power into this problem if you learn how to extract the correct features that then the network can learn and operate on more efficiently. So in my opinion, it is still worth to be aware of this, not just this, but all the other approaches that I have presented, because they can provide you with a transformed data set which is lighter and more informative for your purpose than just smashing all the data into a deep learning network. Okay? Now, back to the classical approach. I applied an edge extractor to this single band data set. I have obtained the edges. Note that obviously the result, the procedure for edge extraction has some parameters that may need to be tuned. It's not as obvious as it looks here. And if you change the parameters, the result also can change. But what I wanted to point out here is that you're factually collecting an aspect of spatial information which may be useful in a context of mapping, for example, because what you may notice here is that wherever you have an urban area in the original data set, you have a lot of white pixels here. So you have a lot of pixels that were identified as edges. So much so that if you take, for example, the local concentration of white pixels, that is a good indicator of whether the area that you're looking at is an urban area or a rural area. So it's a way of preparing a data set which is more suitable than this for classifying the land cover type in terms of urban versus rural. Okay. Obviously, it depends on what you need to identify because if you, for example, if you want to identify the type of crop, this is not a suitable data set. Okay, you can barely tell this is different from this, but you would never be able to say this is corn and this is wheat. Does that make sense? What type of information is more suitable for doing that? Spectral, definitely. Okay, we're talking about spatial here. Urban areas are suitable to be discriminated from rural areas based on spatial information. Why? Yeah, because the edges are there. What does that mean? Because these are non-homogeneous areas. They have edges, whereas these areas do not have as many edges. And this is something that I realize when I compare nearby pixels, spatial information. Okay, let's move forward. Yeah, this was the procedure, just for sake of, out of curiosity. Once you have the intermediate result, and this is quite simple to obtain, you can classify the urban areas by simply looking at the local density of edges. So if you, between this and this, there's a third image, which is basically the local concentration of edges. You take a local window, you compute the local number of edges found within a certain window and a new threshold. And whatever is above threshold is an urban area, and you get this map. So this is a very quick example of what you can do without using deep learning, okay, with a much simpler and lighter approach by simply leveraging basic feature extraction procedures. Okay. Yeah. Okay. Then, spatial information can be useful also in a different respect, which is, I briefly mentioned this earlier. Like any other measurement, when you do remote sensing, the result is subject to errors. Okay. And if you can group together multiple units, multiple pixels that are supposedly belonging to the same length cover class, then you can learn something from their statistics, or you can simply average them out and stop there. But in any case, you're getting a little bit better quality information rather than simply considering the individual pixels one at a time. And this is the matter of, this is the turf of segmentation and superpixel generation, which is also quite a common approach in Earth observation. What does it mean, image segmentation? It means segmenting, partitioning the image into connected and homogeneous areas, generally associated with a specific object or with background. By definition, background is what is not of interest to us. Okay, so it's a part of the data set that we can ignore. But that's one special case. In general, we are interested in breaking down the interesting content of the image into homogeneous areas that we can then process separately. And we have an example here on a standard hyperspectral data set, where what is shown here is a set of segments which were generated by comparing spectral response. In some sense, this is a mix, because in order to generate this segmentation, you're using spectral information, because you need spectral information because you want to see how similar the pixels are among them. Okay, when you decide that there's an edge there, it's because you have looked at the spectral response on one side and the spectral response on the other side, and you decided that these spectral responses are distant enough to say, yeah, there's an edge in between. Okay, so this approach is somehow a mix, uses a mix of spatial and spectral information to carry out this task. Yeah, we have a series of examples here, but finally, just like in the case of edge extraction, obviously, if you change the parameters of the algorithm that you are using, you will also change the final result of the segmentation. And there's a branch of remote sensing data processing, which is called GeoBIA, or Geographical Object-Based Image Analysis, which is somehow the close relative of object-based image analysis in computer vision. And here the idea is, first you identify the objects that are found in a data set, and then you analyze them separately, leveraging their specific characteristics that you may have identified. Obviously, the result, just like in computer vision, the result may not be optimal at the first step, so you reiterate the procedure until you find a correct partition into relevant objects. Like in this case, you separate the forested area from the agricultural land and from other types of land cover, whereas in the first attempt, the forest was over-segmented. Depends on the parameters, but in any case, this is the standard, let me say, the standard way of approaching object-based processing in Earth observation. Okay, now we have deepened a little bit the discussion on on spatial information. Okay, I've not discussed everything. I didn't want to present a long list of possible techniques because I don't think they really matter to them. The most important thing is to pass the concept of what happens in Earth observation and why is it different from, let's say, traditional computer vision. And there's another aspect here which, in my opinion, is worth showing. And I'm still talking about basic analysis in the sense that, again, we're not moving directly to the final result. We are playing with the data in such a way that it's better usable for your application. So this is something that I have implicitly said during the latest lecture. How can we, let's say, identify the right approach to extracting the information of your interest? One distinction that we made clear was between spectral and spatial information, right? The landscape is actually a little bit more complex, but not that much. We have spectral information sits in a multivariate data set, in a multispectral data set. We can do this type of analysis because when we reach out for the filing cabinet, we take the drawer, we pull it out, and we see a number of numbers, right? Not just one. It's multivariate. It's a multivariate data set that we're looking at, okay? And these numbers represent the spectral information. Then we can also decide to use spatial information. When we aim at spatial information, we use a scalar data set. Multispectral data is generated as a multivariate data set, but we know that we can move to scalar by simply picking up one of the bands. We discussed that multiple times. Because if you are interested in spatial information, you go for a scalar data set, and if the data set that you have is multivariate, then you generally select one band of that in order to focus on spatial information. There's also a third source of information, which is implicit in what we discussed earlier, and it's the so-called radiometric information. What do you mean by radiometric information? It's implicit. We're not discovering anything new. Okay, I'm just putting things in context. What does it mean, radiometric information? By radiometric information, I mean the individual information unit that you get from one scalar point. So, for example, radiometric information is the value of the pixel, is the fact that the value of the pixel is low rather than high. Because, for example, this lets you distinguish between water or dry land in radar data. Okay. Now, this is also a piece of information that you put in the mix. Okay, you should not ignore that. We discussed spectral information, we discussed spatial information, but there's also radiometric information contained in Earth observation data sets. And let me skip a couple of things. What do I mean when I say spatial information, how do I see the spatial information? Are you familiar with histograms? I think so, right? So a histogram can be produced also based on a scalar Earth observation data set. You put here on the horizontal axis the value that you're analyzing, so it can be the reflectivity on one specific band of the acquisition, and then you count the number of units which possess exactly that value. And that makes a histogram. And the histogram, well, the theory says that it's an approximation of the probability density function of appearance of that value, et cetera, et cetera. But it's important to focus on the practical meaning of this radiometric information. Because in most cases, you will notice when you analyze a histogram of a remotely sensed data set, even if you're looking at one single band, most likely you will find a situation like this where you have these bumps in the distribution, which are called modes of the distribution. And generally, these modes are linked to the presence of a specific type of length cover. Okay, may or may not be sufficient to distinguish them, but still they represent a clue that, for example, in this case, you're looking at two different types of length cover. It doesn't always work. It's just a clue. It's not a solution to your problem. It's a clue. If you ask for a histogram and you see something like this, then you may conclude, not conclude, but at least suspect that there may be water and solid land, at least. Okay, let me give you an example, which was generated by using SNAP, which is the software that we will see later this afternoon. This is Sentinel-2 band 8, which means infrared. It's again the Mangalore image. Vegetation appears very clearly. Cloud appears very clearly. Remember, this is the reason why we define the vegetation index, because otherwise this is also vegetation. Now, if you request a histogram of the data set, you will notice that you definitely have at least two different homogeneous areas, two different line cover classes. This is, what is this? The C, right. It's homogeneous, so the mode is thin because you don't have much of a difference between the pixels. It's homogeneous and it's big, and indeed. Then you have solid land. In solid land, you generally have, and also in this case is no exception, you have broader variability of values, and you see that here. It's big because the area under the curve is still big, but it's also more variable than the C. Can we conclude that we have two different objects? No. We can conclude that we have at least two different objects. In fact, we have at least three. Because if you look at the data set, you have solid land and you have the cloud, which we didn't correct, so it's still there. This is level 1C. So the cloud is still there, and I cannot tell there's a cloud from this. But there's more to it, I believe. Why did I call it radiometric information? I called it radiometric information because I'm looking at the single pixel. And there's something that tells me that I'm looking at the single pixel, not to the entire image. I mean, I'm looking at the entire data set, right? But I'm not looking at any link, at any spatial information, because I'm just counting pixels, right? I'm counting. I'm not saying anything about their mutual location. So it's not spectral because I'm not using multiple bands. It's not spatial because I'm not looking at the order, at the spatial order of pixels. I'm just looking at values. This is the idea of radiometric information. I'm really looking at the distribution of values. Okay, if you were to scramble all the content of the image, as far as you keep the same values, so suppose you change randomly the order of pixels, this would not change. Meaning that this is completely transparent to spatial information. So it's something else that we're using, right? Okay. Let me move on to a different subject. Which is a mix. This is a mix between spectral features and spatial, spectral features and radiometric features. And this is typically done by expanding the histogram to 2 dimensions. Could do it in principle on multiple dimensions, but in order for it to be visually interpretable, you can only do that with 2 bands, possibly 3, but not more. So the idea here is that you can build a histogram based on 2 variables. So you take 2 bands, not just one band number 1, band number 2, and then you use them to define 2 axes. And you count, again, you count pixels. You count how many pixels possess this value on band 1 and this value on band 2. And then, okay, 2 questions. I should have asked this earlier. What can I count? Isn't this a continuous axis? Is it continuous? No, it's not continuous. Why is it not continuous? So why does it make sense to think of a finite set, which you can count, and not to a continuous variability of, after all, I'm estimating reflectivity, right? Reflectivity or spectral reflectivity. It's a physical variable. It's continuous. Why can I assume that I'm working with discrete values? Sorry? That's spatial. That's spatially discrete. I think if I correctly count your observation, it's spatially discrete. But my point is that it is radiometrically discrete. When you use a sensor, the product of the measurement is a binary code word. It may be several pixels long, but it's still binary. It's discrete. So even though the variable that you're estimating is a physical variable, it's continuous, but the reading itself is discrete. And it is reflected in a limited set of possible values that can fit into any band. Typically, I briefly touched on this at the beginning when I said typically you use 12 to 16 bits to represent the value in a given band, et cetera, et cetera. Okay, so 2 to the power of 12 means 4, if I'm not wrong, means 4,048 different values, full stop. So it means that this is not a continuous axis, this axis only possesses 4,048 different possible locations where pixels can be found. Okay, so you can count them. Okay, you can count how many possess exactly that value. You can do that for both sides. And where does the count go? Because we have already exhausted the space. We have exhausted the axis. If this is a plane, and a screen display is a plane, okay, so far we haven't hologram displays yet, at least not commercially viable. So how do we deal with the third axis? Well, using a simple trick, which is that of defining color. We use colors to mean the frequency with which a certain pair of value will show up. So where you have the background color, there are no such combinations, and most of the graph will be covered with no combination. But then, typically, as you move to the bisecting line, as you move towards the bisecting line, the samples will start appearing, and higher frequencies will be associated with maybe brighter color or whatever else you can use. Remember that you're doing visual interpretation here, so you don't need to be rigorous because you're just looking at how the data looks, and you're trying to draw some conclusions based on your visual interpretation of this, of the output. Okay. So this graph tells you, for example, that most pixels on these two bands will have similar values. Why? Because most of the samples are on the bisecting line, x equals y. But there will be some combinations that are much more frequent than others. And this is a typical case in Earth observation data. Most of the values, most of the pixels will be concentrated around the bisecting line, which means that, especially if you consider adjacent bands, in a multispectral acquisition, you will frequently find a situation like this, meaning that the two nearby bands are correlated with each other. Okay, a graph like this indicates correlation. If you have a certain value of variable x, the value of variable y will never be too different. That spells correlation, okay? Correlation in multi-band data is frequently a problem with Earth observation data. What can I do with this type of analysis, this type of radiometric features? Well, one kind of analysis that I can typically do, but this is just an example, but if we take once more our multispectral image on Mangalore, and we analyze, oh, I've almost exhausted the time. If we take that image and we, for example, analyze band 3 and band 4. Band 3 is green and band 4 is red. We find that after all, they're not too different. See, most of the values are concentrated around the bisecting line, but some others are not, but not so many. But the interesting part comes when you analyze band 4 and band 8, compare these two. So again, you have a lot of correlation, but then you have a cluster of pixels, which a relevant amount of pixels, which do not show such correlation. Do you have any clue of what this is? We don't know where they are. We don't know because in moving from the data set to the scattergram, so-called scattergram, we have lost the spatial information. But based on the radiometric information, so based on the fact that these pixels correspond to an area where the infrared response, this is band 8, infrared response is much stronger than the red response, what can I estimate it may be? No, because the cloud is strong also in terms of red reflectance. No, this is something else. Vegetation, right. This is vegetation. So by looking at the scattergram, you realize that most of the pixels are correlated, but those who escape correlation, because they have high values in one band and low values in the other band, these are probably vegetation. So I'm looking at an area where I have, well, some type of correlated line cover, and then I have vegetation. Okay. So again, this is something that tells you a little bit more, because you're using also a little bit of spectral information. This is something that tells you a little bit more than just looking at the one-dimensional histogram. Okay. Now, let me see. I think this presentation can be closed here. We still have about 10 minutes. Let me see if I can tell you something more interesting about a specific type of transformation, which is a spectral transformation. Spectral transforms. So I mentioned earlier that many methods and algorithms fall under the hat of transformations. And these include transforms, so which means rewriting the data, as I said previously, rewriting the data in a manner which is more useful for your purposes. This includes a specific category of transforms, which basically repeat the same information, but it writes it differently. Obviously, you know the difference between data and information. Now, what you get from the instrument is data, but what you are seeking is the information hidden in such data. You can play with the data and conserve the same information. And this, so you write the numbers in a different manner, but they're still telling you the same thing. Except if you do this in a right manner, they will tell you more clearly the type of information that you're looking for. So the transforms are specific, are a special, not a special, I would say, are a good example of this. So if you have a let alone non-linear transformations, which are way too complex to deal with here. Let's focus on the so-called linear transformations. If you have your data set, your this is the drawer, okay, from the filing cabinet, numbers. I put them in a vertical vector. I put these numbers into a vertical vector so that I can use the matrix algebra on it. A transformation, what is it? A transformation, a linear transformation, can be defined by a matrix of coefficients which multiplies this vector, and it gives you a second vector, which is a transformed vector of this. Why are we interested in this? Okay, why are we interested in picking up again on maths, on the matrix algebra, and so on and so forth? Okay, let me explain you one thing. There's one truth that needs to be said and clarified about multispectral data. We said acquiring multispectral data means looking at different wavelengths, measuring the same thing along different wavelengths, right? We have already had some clues of the fact that these measurements are not fully independent. What do I mean? I have a series of numbers in the drawer, but these numbers, we're looking at the same object, so they're obviously linked with each other, but they are more strongly linked than we can believe. What is the reason? There's a physical reason. When you're measuring a specific object with a specific reflectance curve, that reflectance curve, since you're looking at a physical object in the physical world, it doesn't change too abruptly. Like any other natural phenomena, it changes smoothly. Okay, so if you sense it here and then you sense it again here, you shouldn't expect it has changed a lot from the first to the second measurement, and then to the third, then to the fourth, etc. Ultimately, it is going to change, but it will take several samples, several spectral samples. Spectral information tends to result in correlation across the physical reality, tends to generate correlation across the samples. Okay. Plus, there are other factors which generate correlation. Well, these are too technical. I don't want to delve into them. Let me point out that if you don't do anything about that, it is unavoidable that when you acquire a multispectral, or even more so, an hyperspectral data set, because you're looking at samples that are really close to each other, you generate a lot of correlation within these data. Okay, from the simple fact that you're looking at a slowly changing thing, and you continue to interrogate it multiple times. This correlation is harmful to your computation, is harmful to your information extraction process. Why? Because, in some sense, every time you have correlation, you're in some way or the other repeating the same information over and again. Okay. So, in some sense, you're using multiple, or you're using a lot of storage space to simply repeat the same operation. And that would be still bearable, but then there comes another factor, which is called the curse of dimensionality. Some of you know about this. It means that you're basically the fact that you're using multiple samples means that you're implicitly generating an hyperspace with a lot of dimensions, which becomes a curse when you want to do, for example, classification on this data set, or when you want to do learning on this data set. Because you have an hyperdimensional data space, which is extremely difficult to capture for any approach that wants to systematize the data, be it classical or deep learning based. How can you, I mean, you have a number of training samples, but these training samples become increasingly rare. They don't change, they're still the same, but the space in which you put them, in which you're trying to characterize them, gets bigger and bigger and bigger as you add samples, right? That's the essence of the curse of dimensionality. If the dimension of the variable space is huge, then my set of training data becomes too small to train anything. The reason why, this is the reason why classification using whatever approach fails if you use correlated data, because you can't get decent training, or you can get a reliable set of parameters for a classical approach, because you're looking at an incredibly empty space with very, very few samples. So this is a problem. This is a factual problem in Earth observation. It's a problem for multispectral data. It's even more so for hyperspectral data. So what can you do about that? That's the idea behind using spectral transforms, and specifically the so-called principal component transform, which in essence builds a matrix, note well, an invertible matrix, which turns this data space into a new data space where by design, all the dimensions are uncorrelated with each other. Does that make sense to you? I multiply the original vector, the multispectral vector, times a suitably designed matrix to get a new vector, which is defined in a same-sized space, but where each and every dimension is completely uncorrelated with any other. Okay, so in this case, I'm somehow removing, no, not somehow, I have removed the correlation completely. And I have also obtained a new representation of the data where most of the information is concentrated in few bands. Now, the new data set that you get can be translated back to the original data set. I have not destroyed any information because the matrix W is invertible. So if I take the new vector and I multiply it by the inverse of the matrix W, I get, apart from the numerical approximations, I get, again, the same vector I started from. Okay, so I have not destroyed any information. I can rewind exactly the operation. But if I stick to it, okay, so if I stick to the new multi-dimensional representation and I look into it, wow, we'll try and summarize as much as I can. If I look into this space, I will realize that I have concentrated, with this operation, I have concentrated most of the information into a few bands. I think I have examples here. Yes. So look, this is visual representation of a multispectral data set. You can, even visually, you can tell the correlation. All the images look like each other. Whatever is bright in one image tends to be bright also in the other images. Look at this area here. Look at the shadows. shadowy areas are dark everywhere. Okay. Now, after I have carried out this transformation, I have principal component number one, the first axis in the new data space, which is the most informative one. This is the one that contains most of the information. It looks like most of the previous, but then I have a axis number two, which contains completely uncorrelated information. With respect to the first one, see, the aspect has changed completely. And I'm talking about radiometric aspect, not spatial. Naturally, in a spatial sense, it looks like the other one. The shape is the same, because I'm looking at the same area. I have transformed it radiometrically, not spatially. But see, these layers are completely uncorrelated with respect to the others. And if I go on considering the other layer, the successive layer, I realize that I'm looking at noise. I have removed the correlation, and at the same time, I have pushed the information to a few bands and noise to the other bands. So this is a great result because it means that I can process a smaller number of bands, I can save computation power, I can save storage space, and I still have my information, almost all of my information still sitting there. So I can still extract it, but with less effort, with generally less effort than I would have had to do with the original data space. Now I think I have to stop here because I passed the time once again. So thanks again, and we now take a break and we reconvene up in the lab, just like yesterday. Okay, thank you. Yeah. This afternoon we will try and use the SNAP software, which needs the installation basically. So Professor Gupta will give you the software. I think you can trigger the installation even while we are doing the exercise on the browser, because this will run independently. So you start the installation, and then we start as the installation rolls, we do the exercise on the browser.